This video will show how the analysis of the area under a velocity versus time graph can lead us to one of our primary kinematics equations. We begin with a simple velocity versus time graph, and considering the idea of a constant acceleration. We have an initial velocity, v0, and over a course of time we extend to some final velocity, v final. From this we want to show how to get to a mathematical expression for the position. So what we can do is take the area under this graph, and we see that there are two sections that we need to analyze. There's going to be the triangular portion here, and there's going to be the rectangular portion here. So we take each of these separately, and the first one we'll consider is the area 1, and this is just going to be a length times a width. Second piece we consider is area 2, it's the area of a triangle, 1/2 the base times height. So when we look at how these show up on our graph, the length times width for the rectangle is going to be a length, we could say this height here, of v0, from 0 up to v0, and then a width of delta t, t0 to t final. So that's this piece here, and then 1/2 the base times the height. Our base, we're saying, is delta v. Our height, we're saying, is delta v. So this is going to be a change in velocity from v0 up to v final. And then again, our extent of our graph, this time the base, is going to be that same delta t. So here we write 1/2 delta v times delta t. So now we're going to make a substitution in order to simplify this, and we're going to call upon our definition of acceleration right here, which is acceleration being equal to delta v over delta t. And we want to make a replacement for delta v. So a simple rearrangement of this expression says delta v is equal to acceleration times delta t. We'll just take this a delta t and put this right in here. And when we do that, we have this a delta t times delta t. So now we have two delta t's, so that makes it a square. And our final expression at this point is delta x is equal to v0 times delta t plus 1/2 a times, should be delta t squared here. The way we're going to simplify this at this point, make it more generalizable, I would say, is we'll rewrite delta x as x minus x final minus initial position x0, and delta t we will write as just t, assuming from our graph here that our initial starting time is 0. So therefore t final minus 0 is just going to be some value t. So with delta x here on the left rewritten as x minus x initial, we're going to add this x initial back to the right side, and we get the final expression now of your final position is equal to your initial position plus a piece due to the velocity. So the fact that you already have an initial velocity, multiply that by time, that gives you a further extent of x. And then finally, if there's an acceleration piece, then we have to do 1/2 the acceleration times time squared, where this 1/2 in this case has come from the triangular portion, 1/2 base times height. And we see that this expression matches with the one that we showed from lab number 3 with the ball rolling down the ramp. So this is how we can get to one of our primary equations of motion. And it also shows us a way to calculate displacement without even needing an equation of motion. Simply by taking the area under this velocity versus time graph, we have a powerful method for determining the displacement of an object.